Okay, so this is part 2 of lecture 20. I'm gonna solve problem 3. Again, I encourage you to try to solve it on your own before looking at the solution. The problem says consider a 3-node trilinear brick element, and then this is the element in the physical domain coordinates x, y, z, and then we are sketched out the parent domain. So this is parent domain or parent element in the coordinates xi, eta, zeta. And we are asked to write the shape functions in terms of the parent domain coordinates xi, eta, zeta. We need 8 shape functions, and it says remember that you can write them as a product of one-dimensional shape functions. Hopefully you remember. But what are the 1D shape functions for the linear element? So if you only had xi, xi from -1 to 1, the first shape function would be like this. Well, that's so terrible. The first shape function would be like this, so that would be n1 in 1D. So it will start at 1, go to 0. The other shape function will look like this. So that will be n2 of 1D, and we can write it out. So n1 of 1D of xi. That one would be, if you remember how to write these ones down, this is just 1 minus xi over 2, and then the second shape function, it's a function of xi, is 1 plus xi over 2. So note that if I substitute -1 here, then 1 minus -1, that's 2 over 2, that's 1, so it starts at 1. And then if I substitute +1 here, then this is 0, so it goes to 0. So n1 is correct. And then n2, if I put -1 here, I get 0. And if I put +1 here, I get 2 over 2, 1. So n2 is also correct. So those are the 1D shape functions. Now how can we use those to get the 8 shape functions here? So let's start with the first node. The first node right there. Note that that first node is in the -1, and I should say, but here it says that every one of these coordinates goes from -1 to 1. I guess the sketch is not very clear, but this would go, so this point right here would be the point with coordinates -1, -1, -1. So that point actually, so the n1 of 3D, because it's in the -1, -1, -1 position, it will be the product of the n1 shape function, but in terms of xi, eta, and zeta. So this will give you 1, actually let me do the 1/8 outside. So this will give you 1/8, and then similar to the n1 shape function, but for all 3 coordinates. So that's the first shape function. So that's the shape function that corresponds to the orange node right there. So let's look at the second node. Second node has coordinates 1, -1, -1. Now because that one has 1, -1, -1, you can guess what is going to be the shape function here. So it's going to be the second shape function for xi, but still the first shape function for eta and zeta. So that's the second node. Then the third node right here, that one has coordinates 1, 1, -1. So you probably can guess that this will give you, you will need the coordinates corresponding to the positive, so second shape function in terms of xi, second shape function in terms of eta, but first shape function in terms of zeta. And that's that guy right there. Then N4, that's this guy right here. That one has coordinates 1, 1, sorry, minus 1, 1. So it's in the negative psi, but in the positive eta, and then minus 1. So minus 1, 1, minus 1. So that means that the shape functions in terms of the parallel domain coordinates are going to be minus 1, 1, minus 1. So 1 minus psi, 1 plus eta, 1 minus zeta. So that would be this guy right here. And then I'm going to spare you the entire process. So the other shape functions look kind of the same. Let me move this up a little bit. They look kind of the same, but the only difference is going to be the last. So these are all going to have plus. So those are the shape, the 8 shape functions in terms of psi, eta, zeta. Why am I going there? So that's this. Then write down the isoparametric map that is express x, y, z as a function of psi, eta, zeta. So this is not more complicated than what we do in 1D or 2D. It's always the same. So x is just that we have 3 coordinates. The x coordinate is sum of shape functions, the 3D shape functions, so from 1 to 8, which are in terms of psi, eta, zeta, times the x coordinate of the nodes. So in this case, 8 nodes, 8 x coordinates, 8 shape functions, and the shape functions, because we're in 3D space, they're functions of psi, eta, zeta. Then y is just going to be the same, so sum from 1 to 8 of the shape functions that we just defined in terms of psi, eta, zeta, times the y coordinates of the node, and then zeta again, sum of shape functions times zeta coordinates. So this basically relates a point in the xyz space to a point in the psi, eta, zeta space. So that defines basically this switch between xyz and psi, eta, zeta. So that's the isoparametric map. Write down the Jacobian, that is the derivatives of xyz with respect to psi, eta, zeta. And then this is also similar to what we did in 2D. So this is basically the partial of all the x coordinates with respect to all the xi coordinates. So it is some matrix. In 1D this just has one element, right? Because you only have x with respect to xi. In 2D this was a 2x2 matrix because you had xy with respect to psi, eta. In 3D this is going to be a 3x3 matrix. So this is going to be 3x3 matrix. Each column here is going to be with respect to a different coordinate. So this is going to be derivative of x with respect to psi, derivative of x with respect to eta, derivative of x with respect to zeta, and then just copy but it's gonna be y and z. How do we calculate these ones? It's gonna be a lot of just repeating, but let me just make this a little bit tight here. So derivative of x with respect to psi, that's just taking this derivative. So that would be sum of partial derivatives of the shape functions with respect to psi times the x coordinate, then derivative of x with respect to eta. Again, sum of partial derivatives with respect to eta, and then sum of partial derivatives with respect to zeta. So again, note that I want derivative of x with respect to psi. I have x in terms of the three parent domain coordinates because I have the shape functions. So if I want to take the derivative of x with respect to psi, all I need to do is take the derivative of this expression right here. So the sum of the shape functions times the nodal values. The nodal values are not functions of anything, so those I don't take derivative. And then the shape functions are functions of psi eta zeta. They are defined right here. You know, all 1 through 8. So I need to take the partial derivative with respect to psi times the x coordinates, the partial derivatives of the shape functions with respect to eta times the x coordinates, the partial derivatives of the shape functions with respect to zeta times the x coordinates, and repeat for so this looks exactly the same but for y, and I'm not gonna write the z. So this is y, and then just do dot dot dot. Right, so this is the Jacobian, and this is something that you can evaluate for any particular psi eta zeta, because you have basically at the beginning you have the shape functions and you have the nodal coordinates. So given the shape functions and the nodal coordinates, you can evaluate the derivatives of the shape functions at any psi eta zeta, and sum times the x, y, z coordinates, you get the Jacobian. So that's something that you can compute. And I think that's all it asks for. So write down the Jacobian matrix, yes. How will you interpolate temperature field inside of the element given that you have the nodal values? And then we are going to express the temperature field in terms of psi eta zeta coordinates. So this is function interpolation. So that means basically we have our cube, and then we are given some values, T1, T2, T3, T4, T5, T6, T7, and T8. So Ti are temperature values at nodes. So given that we know the temperature values of the nodes, we can express the temperature field, so interpolate the temperature inside of the element by using the shape functions, just as always. Temperature equals, so the interpolation of the temperature is going to be the sum of the shape functions, in this case 8 shape functions, which we just wrote down, and they are functions of these 3 variables, times the temperature at the nodes. So that's how you would interpolate. So given that you know the temperature values at the nodes, just evaluate the shape functions at any psi eta zeta, right? So if you put in, for example, psi eta zeta equals 0, 0, 0, then you would be evaluating the temperature at the center of the quadrilateral. But you know, you can pick any value of psi eta zeta within -1 and 1, and then basically you are evaluating the temperature somewhere inside of that cube. So that's how you would evaluate the temperature. And then that's it. And then finally, what if you want to compute the gradient of the temperature? And note that the gradient means derivatives with respect to x, y, z. So this is something that I did a video just before spring break on this, so go check that out. Basically what I showed in that video is that if you want the partial derivatives with respect to x and y, I did it in 2D, so just x and y. Here we have 3D, but you can imagine that this is exactly the same as before. So you need to do the chain rule. You need temperature with respect to psi eta zeta, and then derivative of psi eta zeta with respect to the xyz, and that is the inverse of the Jacobian. So here you have inverse of the Jacobian times the gradient with respect to the parent domain coordinates. So the gradient with respect to psi eta zeta. So if you can calculate the Jacobian, you just need to take the inverse. And then how do you calculate these gradients? Well, you have the expression right here, so just take the derivative of that. So this will be sum of partial derivative of the shape functions with respect to psi times nodal values, sum of partial derivatives of the shape functions with respect to eta times nodal values, sum of partial derivative of shape functions with respect to zeta times nodal values. So that's how you would calculate the gradient by using chain rule. So you need inverse of the Jacobian, and you need to take derivatives in psi eta zeta space. That's it. This is basically the same as the lecture that I did in just before spring break. And I'm uploading this PDF with the